Okay, so the next speaker is Yongxiao Lin from EPFL. He will speak about averages of coefficients of GL3 times GL2 L functions.
Okay, thanks to the organizer for giving me the chance to speak here. So this talk is based on joint work with Qingfeng Sun, who is at China's Shandong University Weihai campus. So to motivate, let us first recall the notion of level of distribution. So suppose we have a sequence of arithmetic function, lambda f of n, and we'd like to ask how uniform these sequences are distributed among arithmetic progression. Namely, we'd like to ask if we consider this average over arithmetic progression subtracted by the expected momentum. Here, phi is the Euler phi function, and we'd like to have a smaller error term. What we specifically want is this modular Q should be taken to be some power of x, and would like theta to be as large as possible. So here, this exponent theta is called the level of distribution. So we'd like to restrict ourselves to the case that this coefficient lambda fn should be Hecke eigenvalues of some automorphic form f defined on GLD. So for example, if we use the Lin's estimate for hypercustom sum, then we can get an exponent theta equal to, say, 2 over d plus 1. Again, here d is the rank of the automorphic form. Let us consider one example. If we consider the GL3 automorphic form, if the automorphic form is the isobaric sum of 1, 1, 1, this kind of Eisenstein series, then the coefficient amount to, say, the triple divisor function. And this trivial exponent should be equal to 1/2. And proving exponent better than 1/2, this amounts to the groundbreaking work of Friedlander and Ioannis in the 80s. And there are subsequent work by Hisbrown, Kowalski, Michel, and Pincy. If we consider another case of automorphic form on GL3, the isobaric sum of 1 and a GL2 cast form, then an exponent better than 1/2 is proven by Kowalski, Michel, and Sawin. So today we are not going to discuss this problem. Rather, we would like to ask a short interval version of this problem. So we would like to ask an analytic counterpart how short this interval can be taken so that we still have this asymptotic formula. Here, depending on whether the L function attached to the coefficient has a pole at 1 or not. If there is, then we have an expected momentum. Otherwise, we do not have a momentum. Equivalently, we would like to ask how small can we take this asymptotic formula, can we take the error term to be, so that we still have this asymptotic formula. Here, A sub d denotes the average of the coefficient up to capital X. Well, what do we know about this average? Naively, we may expect that the error term can be taken to be slightly smaller than the length of summation X. But actually, much more is true. So there is a general result of Friedlander and Ioannis, which states that we have this error term. The error term can be taken to be x to the d minus 1 plus over d plus 1. Again, here d denotes the degree of the L function. So if we assume GRH, then we can get the error term to be square root of the length of summation. A natural question is how to surpass this exponent. So in this talk, we will consider a case of GL6 automorphic form, the Rankin-Silver convolution of a GL3 cast form against a GL2 cast form. So what will be the coefficient. So let's recall if we denote lambda Rm be the Fourier radical coefficient of the GL3 class form, and here lambda f of m to be the coefficient of the GL2 class form. Then the Lonking-Searberg air function is defined in this way. And the coefficient of this lambda f is given by this form. Then we restrict ourselves to this GL3 called GL2 automorphic form. The aforementioned result of free lambda and E1 is states that we have this error term x to the 5/7. And in this case, the Lonking-Searberg air function does not have a pole at x equals 1, so this main term does not exist. So we only have this error term, and our result states that we can get an exponent slightly better than the 5/7. So how should we approach this problem? So before we go into our proof, let us briefly recall the strategy of free lambda and E1 in getting this error term. Again, let's recall this summation, and an observation by free lambda and E1 says that the study of this average can be reduced to its dual sum involving the dual form. So here lambda f bar is the complex conjugate of the original coefficient twisted by some exponential function, and inside the exponential function is a phase looks like this form. So here D again denotes the degree of the air function, and here x is the original length of summation, and n is some parameter. Here v is some smooth test function. More precisely, by applying functional equation, they obtain the following nice identity. So here the original sum can be related to a dual sum B via this identity up to an error term of this form. And n is some parameter to be chosen at our disposal. So in particular, if we estimate the dual summation B trivially by, so recall B is like this form, we can estimate B by just the length of summation. Here this factor times n, and then we choose n appropriately. Then free lambda and E1 is get their general error term x to the d-1 over d+1 under a mild assumption on the spectral parameter on the air functions. So we should also mention that if we assume the coefficient that we are summing over are non-negative, then Landau's lemma also provides a similar error term. So let's recall again, the dual summation looks like this form, and in their paper, free lambda in E1 is conjecture that we can estimate this summation by any epsilon power of the parameter, and correspondingly, they make the following conjecture that the optimal error term should be taken to be x to the d-1 over 2d. So we couldn't make any progress toward this conjecture. Rather, we would like to improve over the trivial error term. So according to the identity of free lambda and E1 is this identity, if we want to improve the original estimate for this A sub d, it suffices to give some improvement for the dual summation when n is in certain range. So we would like to improve this trivial estimate when n roughly equal to this size. And we consider the case that d equal to 6, and the automorphic form is the GS3 times GS2. So let us set more generally the following summation. Here is the GS3 called GS2 summation, and the length of summation is of size n. And here we normalize this phase so that this phase is roughly of size 1, and the oscillation of the exponential function is of size t. So our result says that if we specify phi to be the logarithm and or either x to the some power with this power less than 1/3, then we have this upper estimate for this smooth summation. So this upper bound is non-trivial, less than capital N, provided the length of summation is greater than the size of the oscillation rise to this power. We also remark that if we consider an algebraic setting, the algebraic twist, if we replace this exponential oscillating function by a trace function k modular q, then a result of Michia, Sawing, and myself says that we have this non-trivial estimate, provided the length of summation capital N is greater than the modular of the trace function q rise to this exponent under some assumptions on the trace function k itself. So if we apply this result to the identity of free length in E1, then we immediately get the improvement over the average of the coefficient. So actually, this kind of result was first studied by Yongxiao, who considered the case that the phase function phi is the logarithmic function. So if we go back here, if we take phi to be the logarithmic function, then this exponential function reduced to the m to the it. And by using this estimate together with the standard technique in number theory called approximate functional equation, Yongxiao deduced the following subcomplexity result in the T aspect for the GL3 cos GL2 air function. So here T to the 3/2 is the convexity bound, and then he can get a power saving. So our estimate for this analytic twist is better than Yongxiao's upper bound. So correspondingly, we can get a slightly refinement over his exponent. So how did Yongxiao prove his result? So Yongxiao proceeds by using the Duke Freeland Iwanis data symbol method to separate the oscillation of the GL3 coefficient with the GL2 coefficient. So by using this symbol to separate the GL3 and GL2 together with the conductor lowering trick. So here this integral has the effect of restricting the distance between n and m to be less than n over some parameter k. And later, he has a summation involving the GL2 coefficient and GL3 coefficient, for which he used the Volney summation formula to dualize them. And then he applied Cauchy-Schwarz Poisson summation, and then encountering some oscillatory integral, and then he used stationary phase together with the third derivative test. So our proof is very similar to Yongxiao's approach. So we again use DFI's data symbol, but without using the conductor decreasing trick. This is an observation originally due to Keshav Agawa, who observed that this phase has the effects of conductor decreasing. So this effect has been already built inside this expression. And then we again use the GL2 and GL3 coefficient, some Volney summation formula to dualize the sum. And then we apply Cauchy-Schwarz, apply Poisson summation, and we encounter a triple integral for which we apply stationary phase together with the second derivative test. And that gives us the improved exponent compared to Yongxiao's result. That's roughly the step of our proof. So let me mention two more examples. So just now we mentioned the GR3 called GR2 case. If we consider the GR3 automorphic form, say if the GR3 can be factored as 1 and a GR2 cast form, namely the coefficient is of this form, then the trivial exponent is actually 1/2, and then we can get a slightly improvement. If we consider another case, the GR2 coefficient square, then a result of Binzhong-Huang states that one can have an improvement over an exponent originally due to Rankin and Searberg. So what's common in all these three examples is that the coefficient lambda fn, they all have factorization. This is really the why we can make the improvement. A natural question arises. So what about for generic cast form? So let us recall this summation. Lambda fn is a coefficient of a degree DL function. We sometimes have a magnitude, and then the L term is of this form. So if we specialize to GR2 cast form, how to improve this exponent? So at the moment, we do not know how to do. And similar question for the GR3 cast form, how to improve the L term 1/2. And we have a similar barrier for the level of distribution problem. If we consider the distribution of the GR3 coefficient in arithmetic progression, and we would like to have this moduli as large as possible up to actually 1/2. So at the moment, we only have 1/2, and to improve this 1/2, it remains a challenge. And a similar question for the GR3 called GR2 case, how to improve the level of distribution 2/7 by a little bit. So we do not know neither. So I think that's all I'd like to talk about, and thank you for your attention.
So thank you very much.